Let's compute the length of a vector. Don't worry if our notations here are expressed in norms, because as mentioned in the previous videos, the norm expressed in this may be interchangeably equivalent to the length of the vector. Nevertheless, they are of the same purpose, but but more formal is the notation for the norm, which of course again still corresponds to the size or the length of the vector. We're using that here. Don't worry about that. You can always interchange the two notations. We have here our vectors x, y, and z in R2, and we have here these components, and we are going to solve for the length of the vector. If we talk about the length of the vector, just for the first two examples, that would mean we're looking at the distance of that said vector from, the point of that vector from the origin, or again, the size or the length of that vector. So for the first one, we have the norm of the length of x is just equal to the square root of the square of the component, the sum of the squares of the components of the same said vector. This is in R2, so we only have until here. So by substitution, the components of your x, we have 2 squared plus 3 squared. That's actually square root of 4 plus 9. Therefore, the length of vector x is actually equal to the square root of 13. If you would like to, you can always place units, but generally it's already okay with this. Or again, generally for some, we have here units because we're talking about the length. Okay, so or again, you may remove that for the purpose of understanding the discussions already. Okay, so we're just going to duplicate this in the next few. So for y, this is again, you don't need to start with this portion. You may automatically substitute, but I'm writing that here. The components of y have 3 squared plus the square of negative 4. We have here, we call this one 9, plus 16. You'll have square root of 25. So the norm of y is equal to 5. Again, the length or the norm of a vector should be greater than or equal to 0, or positive, or at least 0. So that's very clear that we only take 5 here. Now, moving forward to the last two examples, here for the norm of the sum of x and z, you can always start with the sum of x and z first. So let's start with that sum. Okay, so we'll have here the components of your x is 2 and 3, plus the components of your z, which is 5 and 1. This would mean we have here 2 plus 5, 3 plus 1. You have here 7 and 4. You can automatically add if you would like to, but nevertheless, I'm showing here the steps. So from this, if we're talking about the length of that vector, because we know that vector addition is closed, so the result is still a vector, so the length of that is still this one here. So let me automatically substitute 7 squared plus 4 squared. You have here 49 plus 16. And that is equal to square root of 65. Okay? This is the result for the norm of the sum of vectors x and z. Now, let's proceed to the last one. And I'll be showing you two methods here. Okay, the first method is, of course, if you would like to start with 3z first, that's scalar multiplication of your z, which is 5 and 1. Again, that's correct. Okay, 5 and 1. So you will get here 15 and 3, right? So if you're going to solve for the length of the resulting vector, actually, again, it is 15 squared plus 3 squared. You'll get here 225 plus 9. Okay? So you will get here square root of the sum of that is 234. Okay? So you would like to simplify that if possible. If it's not, then you stick with that. You can actually write this as a product of 9. It's divisible by 9, yes. 9 times 26. Okay, let's check. 9 times 26 is, yes, it's really 234. So with that, since 9 is the perfect square, you will get here 3 square root of 26. This is the length of your resulting vector 3z. Again, vector scalar multiplication of vector is still closed, so this is still a vector. Now, this is the first method. I told you I will be showing the other method. The method would be the method where we apply the property. Take note in the previous video, if we have here a norm of a certain multiple, let's say that is the expression, just take out c and take its absolute value times the norm of vector x. Okay, that's the this is true for all x in R2. We have proven this in the previous video. You might want to review that, because here we have 3z. If you don't want this, then you can apply the property. If you would like to stick with this, then it's okay. But I'm showing you this too, so that you can compare the results. Because here, this just means is take the scalar 3 and just get the the length of z itself. So we know this is already 3. It's already here, almost there. So the z is actually the square root of the components of z, which are 5 and 1, or the sum of their squares. So sorry, that's 5. Let me rewrite that. Plus 1 squared. So you will have here 3 square root of 25 plus 1. Still you will get 3 square root of 26. Now it's up to you which you will use, whether this property, which will get the same result as the previous method where we started with a scalar multiplication before the solution using the length. Now there are some importance or implications of this, because if you're going to use the property, and if you're familiar with that, it's shorter. If you're going to use this method, it's longer, and there might be, I'm not saying there is, but there might be chances of making mistakes in the step-by-step process. Probably mistake in multiplying, mistake in adding, or taking the square root, right? So just like here, the square root of 234 can still be simplified. So you need to look for perfect square factors for you to be able to simplify that. But if you're going to use the property, you don't need that process, because automatically you can take out the scalar per property. Okay, this is how we solve the length or norm of vectors, or which also includes the results of vector operations. Thank you very much for watching.